Okay, guys, so let's take a look at the chapter 5 material. And as I mentioned, the reason why you guys basically had 2 weeks for this assignment, even though it's only 17 problems, this is a bit chunkier. There's more, we're getting into some of the actual math that we haven't been doing as much of up to this point. And so we want to take some time and make sure we really understand this. Again, make sure you click here to get that point. But let's start with the first question here. And suppose our statistics professor tests grades as z-scores. So now if you watched the video that explained what z-scores are, if you didn't, it's in Canvas linked above this recording. I'm going to quickly remind you. The z-score tells you, in terms of number of standard deviations, how far you are from the mean. So if I gave you your test grade as a z-score and I said your z-score is 2, that's telling you that you scored 2 standard deviations above the mean. All right, so we got a 2.20 on the exam. So what does that mean? The score was 2.20 standard deviations higher because it's positive. So we want to choose option C. The average score on the stats midterm was 72 points with a standard deviation of 6 points. Our z-score was -2. We want to know how much we scored. So let's go here. And we're going to say our z-score formula, if you remember that we discussed, is the z is equal to your observed value x minus the mean over the standard deviation. So I'm plugging into this formula. I know my z-score was a -2, so I'm going to put the -2 here. I don't know what the score is, that's what we're solving for. Minus the mean, well, the mean here is 72 because it says the average score was 72. Over our standard deviation is 6 points. Now this gives me an algebra equation. And if you remember, in order to solve these types of equations, what I'm going to do here is I am going to multiply both sides of the equation by that 6 so that it cancels here. So I'm going to go 6 times -2 is -12 equals x minus 72, like so. And then go and add the 72 to the other side. And so adding this, we would get 60 is equal to x. So that's the way to solve it, like an algebra equation. Notice that I also could have just taken the standard deviation, which is 6, and said this represents 2 standard deviations below the mean. So 2 6s below the mean would be 12 below the mean, so 12 away from the 72. Either way, I get to the 60. So let's go ahead and plug in that there's a score of 60 points there. A town's January high temperature averaged 38 degrees Fahrenheit with a standard deviation of 8 degrees, while the July is a 73 and a standard deviation of 7. In which month is it unusual to have a day with a high temperature of 55? Okay, let's figure out what that z-score would be for each circumstance. So we're going to treat this one as our first one. So let's go over here and say the z-score there would be the average of 55, this individual score of 55 minus the average of 38 over the standard deviation of 8. And so if I now take 55 minus 38 and then divide by 8, we get 2.125. So here, my z-score would be 2.125. Now, let's do the second one as a z-score. So I'm going to go z is equal to the same score, 55, but this time I'm subtracting the temperature of 73, which is the average, and the standard deviation of 7. So we're going to go back over to our calculator again, and we're going to go 55 minus 73, and then divide that result by 7, and we get negative 2.57. Okay, in terms of deviation away from 0, 2.1 would be less than 2.5. So this is a more unusual score. Now, I don't care about the fact that it's positive, negative, whatever. This is further away from 0. The mean score would be 0. So we would say it is more unusual to have a day with a high temperature of 55 in July. A high temperature of 55 in July is 2.57. Whoops. 2.57. Standard deviations below the mean, and a high temperature of 55 in January is only 2.13. Now, by the way, z-scores are always given to 2 decimal places. So I'm going to always round a z-value to 2 decimals. Unless, of course, my stat lab doesn't like it. Let's see what we did. That right? 55 minus 38 and divided by 8. That should be right. 55 minus 7.
3.
What's that?
It says round to 3 decimal places.
Oh, thank you for catching that. I didn't catch that. 2.125. I don't know why they did that, because these scores usually are rounded to 3 decimal places, and everything that I give you in Canvas is going to ask you to round to 2 decimal places. So z-scores are usually always 2 decimals. Okay, so now we got the 3rd decimal on there. Let's check our answer again. Thank you very much.
You're welcome.
Okay, let's get rid of this. The mean weight of a breed of yearling cattle is 1103 pounds. Suppose that the weights of all such animals can be described by the normal model. This means this is the mean, and this is the standard deviation. This is, if you recall function notation, this is saying the normal model with the first parameter is the mean, and the second is the standard deviation. How many standard deviations from the mean would a steer weighing 1,000 pounds be? So we're going to calculate the z-score. So we're going to go z equals 1,000 minus 1103 and divide by 72. Now I'm going to do this all in one. I'm going to use parentheses, 1,000 minus 1103 and divide by 72. We get negative 1.43. So I'm going to drop the negative because that's implied here with the below statement where it says below the mean. So it's 1.43 below the mean. Which would be more unusual, a steer weighing 1,000 pounds or one weighing 1,250? Well, let's get the z-score for 1,250. So we're going to go z equals 1,250 minus the mean, which is 1103, over the standard deviation, which is 72. So let's go to our calculator. And so we're going to go to 1,250 minus 1103 and divide by 72. And we get 2.04. So the one weighing 1,250 is more unusual because it has a higher z-score than the 1.43. Fuel economy estimates for automobiles built 1 year predicted a mean of 25.2 miles per gallon and a standard deviation of 5.8 miles per gallon for highway driving. Assume that a normal model can be applied, and let's use the 68, 75, 99.7 rule. Okay, so that means if I've got a normal curve My mean should be centered where the average is. So that's at 25.2. And my standard deviation of 5.8 means I'd add 5.8 to that. So that would take me up to 31, I think. And then again, add 5.8, and that's 36.8. And again, add 5.8, and that's 42.6, I think. I'm doing this in my head, guys, so double check me. And then we're going to subtract 5.8. So that would be 19.4. And then subtract 5.8 again, and that would be 13.6. Please double check me. I'm doing this in my head. And then 5.8 again would be 7.8, I think. Okay, so one standard deviation is here, and that's where 68% of my data lies. Two standard deviations is between these two values, and that's where 95% of my data. And then in three standard deviations, it's 99.7. All right, so now notice that all of these have 25.2 in the center. This one and this one both have 7.8. This one has 60 over here on the right. This one has 42.6. So it has to be option C is the one that we, option C is the one that we want. Okay, so once we have that, in what interval would you expect to see the central 68% of autos to be found? So notice that our central 68 is between the 19.4 and the 31. That's the one standard deviation up or down. So 19.4 to 31. About what percent of autos should get more than 31? Okay, now we're being a little bit tricky here. Let's look at this. All right, notice this center here means that half the data is over here and half is over here. And so half of these figures, the 68, is half of it's here, which is the 34, and half of it's here, which is the 34. So if all of this going this way is 50%, but 34 of it is here, then what remains right here would be 50 minus 34. Or what is that, 16%? Now, there are other ways you could divide that up. That's the central idea. I'm just dividing up to see what's left. So we would expect 16% to be a bigger than 31. About what percent of autos should get between 31 and 36.8? Okay, so now if we look here, this between the two standard deviations is 95% of the data, but we've used 65 of it here. So, or 68% of it here, sorry. So 95 minus 68, I'm a little tired tonight, so I'm going to double check myself with the calculator. 95 minus 68 is 27. So that means in this block here and this block here, there's 27, and it's symmetric. So half of that 27 should be in each block, so 13.5. So in this one here, I should have 13.5% of the data, and here 13.5% of the data. Because if you do 13.5 plus 68 plus 13.5, that's that 95 that was in the middle. So between 31 and 36.8, I would expect 13.5% of the data. So we want to describe the gas mileage of the best 2.5% of cars. Okay, let's go back to that picture again. So if 95% is between these two values, then 100 minus 95 is split here and here. That means 5% of the data is split between here and here. Well, if I divide 5 in half, that means 2.5% of the data is in this range right here, and 2.5% of the data is in this range right here and here. Now, it asked, I really don't like the way this question is phrased. And I'm going to explain to you the reason why I don't like how this question is phrased. If I look at this, two and a half percent of the data is here. That means, now this is just 95% of the data is here. So there's still, 95% of the data is here. So when I drew this, I shouldn't have drawn, so this would be all the 2.5% would be everything beyond here. Remember that in 3 standard deviations, it's 99.7. So it's not just between these two values, it's everything bigger, because just between these two values is the difference between 99.7 and the 95. The 95 is here, the 99.7 is the 3. So that means 4.7 is split here and here. So again, if I divide that in half, that'd be 2.35. So 2.35 would be here, and 2.35 would be here. And outside the 99.7, 0.3 is split in half between here and here. So if I split the 0.3 in half, that's 0.15. So that means 0.15 is out here, and 0.15 is out here. All right, so the 2.5% is anything bigger than the 36.8 that's there. So here. All right. The weights in pounds of a breed of yearling cattle follows the normal model, a mean of 1135 and a standard deviation of 90. What weight would be considered unusually low for such an animal? All right, unusually low, if you remember us discussing in the video, that means more than 2 standard deviations below the mean. So I want to know what X value would give me a z-score of -2 when my mean is 1135 and my standard deviation is 90. So again, what I'm doing here is I'm saying z equals my score minus the mean over the standard deviation, and I'm plugging in. So the z I want to be, would be unusually low, would be 2 or more. So -2. I want to know the score. The mean is 1135. My standard deviation is 90. So I'm going to multiply both sides by the 90. And if I do that, I get -180 equals X minus 1135, because these 90s would cancel. And then I'm going to add 1135 to both sides. So I'm essentially going 1135 minus 180. And that's 955 pounds. So any weight more than 2 standard deviations below the mean or less than 955 pounds is unusually low. One would expect to see a steer 3 standard deviations below the mean or less than, by the way, since my mean is 90, or since my standard deviation is 90, just subtract 90 from this one more time to get the 3rd standard deviation below. And that's 865 pounds, only rarely. All right, let's just see here. A forester measured 34 of the trees in a large woods that is up for sale. He found a mean diameter of 10.6 inches and a standard deviation of 4.7 inches. Suppose that these trees provide an accurate description of the whole forest and that a normal model applies. Choose the correct normal model for the tree diameters. So my mean is at 10.6 and the standard deviation is 4.7. So if my mean's at 10.6, that means the 10.6 is in the middle, so we can immediately rule out this one. I'm choosing between B and C. My standard deviation is 4.7. So 10.6 plus 4.7 would be 15.3. Okay, they're both good there. Another 4.7 would be 20. Okay, they're both good there. Another 4.7 would be 24.7. All right, now subtract. 10.6 minus 4.7 would be 5.9. That's fine. There 5.9 minus 4.7 is 1.2, and then negative 3.5. So let's see what the difference here is. So 99.7, 95, 68. And this has the percentages messed up, right? We want the one that has the 68 within the 1st standard deviation, the 95 within 2, and the 99.7 within 3. So I'm going to choose option B. What size would you expect the central 95% of all tree diameters to be? So 95% should be between 1.2 and 20. About what percent of these trees should have diameters below 5.9 inches? Okay, so 5.9 is right here. So now the same thing, this 68 means that I've got 34%, half of the 68 here, and 34%, half of the 68 here. But notice all of this is 50% of the data, right? So I want to know going this way. So if all of this is 50%, I want to remove the 34. So I want to do 50 minus 34, and that gives me 16% of the data that would be below 5.9. About what percent of the trees should have diameters between 10.6 and 15.3? So 10.6 and 15.3, that's 1 standard deviation, so half of the 68, so about 34%. About what percentage of the trees should have diameters over 24.7 inches? So notice that the 24.7 is right here. That's at the upper of the 99.7. Now, remember what I said. If I've got 99.7 here, then that means that 100 minus 99.7, or 0.3, is halved between here and here. So half of 0.3 is 0.15 over here and 0.15 over here. So bigger than 24.7 would be 0.15. Forrester shows the accompanying histogram of tree diameters he used in analyzing 27 trees in a large woods that was for sale. He was justified in using a normal model to analyze the woods. Was he justified in using a normal model to analyze the woods? Explain. Okay, let's take a look at this histogram. So notice that if we look at this histogram, does this bin look like that normal model? Do I see that bell-shaped distribution to it? Well, these are kind of big for the ends. So no, it doesn't really look like it is quite a bell-shaped curve. All right, so let's see how we're going to answer this. What are our choices here? No, because while the histogram is unimodal, it is not symmetric. While the histogram is symmetric, it is not unimodal. That's not quite symmetric because notice that I've got this dip here. See, if I drew over it, I would be drawing something that went like that. I wouldn't quite describe that as symmetric. So I'm going to say it's not unimodal or symmetric. All right, there were 53 competitors in a downhill skiing event. Their times in seconds are shown below, complete parts A through D. The mean time was 104.64 seconds with a standard deviation of 5.49 seconds. If the normal model is appropriate, what percent of times will be less than 99.15? All right, so we need to know what that z-score is for 99.15. So we're going to go right here and we're going to go z is equal to 99.15 minus 104.64 over the standard deviation of 5.49. Okay, so look like that, enter, and we get a -1. So let's go to our bell-shaped curve. That means that our mean's at 0, here at -1. Remember, there's 68% between -1 and +1, so 34% here. So if I want to know what percent of times are less than that, I want to go this way. So I would go 50% minus 34% is about 16%. Okay, that's using the 6899.7 rule. Let's look it up exactly. So what I would do here to look up the value exactly is I can do it one of two ways. I go second and the distribution, and my normal CDF is the key that I'm going to use. My lower, because I want to go from -infinity up to this -1. So the upper is the -1. Z-scores have a mean of 0 and a standard deviation of 1. Now, instead of 16, it's 15.87%, something like that. All right. Now, the second way I could have done it is second distribution, choose the normal CDF again. But this time I'm going to put in the actual values. So my lower is still -infinity, so I'll leave it like that. But then I want to go to 99.15. In other words, I didn't need to get the z-score because I'm going to use the mean of 104.64 and the standard deviation of 5.49. enter, and it gives me the exact same value, 0.1587. So it's 15.87%. Round to the nearest integer, that would be 16. Notice that's pretty close to our 68, 95, 99.7 rule. 15.87 is pretty close to 16. What is the actual percent of times less than 99.15? Round to one decimal place. We just calculated that. So 15.9. Oh, I'm sorry. No, that's not what it's asking. It's asking what's the percentage up here, right? Because these were the actual downhill ski events. So we need to count it up. There were 53 competitors. We are looking for scores less than 99.15. So 1, 2, 3, 4, because this is now bigger. So just 4 out of the 53. So let's go 4 divided by 53. And we get 0.75, so 7.5%. All right, well, those are pretty different, 16% and 7.5%. So let's take a look at this. Okay, so here's our data. If we go over to, and I have not shown you guys how to do this yet, but oh dear, this isn't big enough for me to move. Let me try. There we go. Okay, so if I go over to data, I've put the data analysis tab in here. And I can show you how to do that. That's the easiest way to generate a histogram. What I showed you before, you have to divide it up in bins to generate a histogram. The way that you get that data analysis tab there is hit File and go to Options and the add-ins and the Analysis Tool Pack. You'll need to then hit Go to manage it, and you have to check those boxes and hit OK. And once you do that, that data analysis tab appears here, and then you can generate your histogram. So my input range would be right here. I didn't make my bins. So let's cancel this really quickly and let me make the bins. So we'll go 98 up to, let's see, we're going from 98 to 117. So I need 118 to capture all of it. And 98 is the lowest. So that is 20. So let's go by groups of 4. That should give me about 5 bins. So 98 to 102, and my next one would be 106, and then my next one 110, and then 114, and then 118 should be the upper bin. I think when we do this, we can just put in this upper bin. So I'm just going to click here and highlight the data. And then click here on the bin range and highlight those bins. And then the output range, I'm just going to click anywhere to draw my histogram. And should be able to click OK. And it gave me the frequency chart, but not the histogram. So from that, we could go over here to insert and our bar chart. And we see that we don't have that bell-shaped curve here. We've got a large grouping here, and then this is kind of like a high peak compared to those, and nothing in here, right? So we got a gap. So this is more like almost too little, where this is a really small second peak, but 2 peaks to it. So it's definitely not normal data. So I'm going to go no, because the normal plot is not appropriate. So A. Make a histogram of the times. Okay, so this is what we saw when we made that histogram. What can be seen from the histogram? So we're kind of, because of these data values over here, we're kind of skewed to the right. All right, a livestock company reports that the mean weight of a group of young steers is 1,089 pounds with a standard deviation of 94 pounds. Based on that model, the normal model with mean of 1089 and standard deviation of 94, what percent of steers weigh over 1,300 pounds? Okay, so I can write out my Z-score, or we said we can just go straight to second distribution and use the normal CDF. We're doing over 1,300, so 1,300 should be the lower value. I want to go up to infinity, so I'm just going to do a whole bunch of 9s here. And my mean is 1089. And my standard deviation is 94. And that's about 1.24%. Weights below 1150. So second distribution, normal CDF. This time I want to go negative infinity. So negative 9999999 to 1150. Same mean, same standard deviation. So about 74.2%. And between 950 and 1100. Same mean, same standard deviation. 47.7%. Based on that normal model, mean is 1159, standard deviation is 88. What are the cutoff values for the highest 10% of the weights? Okay, so we want to know if I've got a normal model that's centered at 1159. Over here, this is going to be 0.10. So the item that we used was not normal CDF. Normal CDF would give me this value. I want to do second distribution inverse norm, option 3. So the area is the 0.1. The mean is 1159. My standard deviation is 88. And this is on the right side where I've drawn the picture. So that's 1271.8. The cutoff weight for the lowest 20% of the steers. So same thing, but now I want the weight that's here, if this is a 0.2. So second distribution, inverse norm. This time the area is 0.2, same mean, same standard deviation. This time the tail is on the left. And that is 1084.9. The cutoff for the middle 40% of steer weights. So now I'm looking at the middle 40%. So I want to know what value is here and what value is here so that 0.4 is there. So now notice, first of all, that if 0.4 is there, that means 0.2 is on this side of the halfway mark and 0.2 is on this side. And all of this is 0.5, so that means that 0.5 minus 0.2 or 0.3 is everything up to here. So to get this first value, I'm going to do 0.3 on the left. So 0.3 on the left, and that's 1112.9. And then this is 0.5, and then 0.2 more is 0.7 on the left to get to this value. So we want to do the same thing, but change the 0.3 to 0.7. And that's 1205.1. All right, normal model, mean is 1103 and standard deviation is 82. So the 58th percentile. Okay, so again, for the 58th percentile, what I'm doing is I'm saying, if I have a normal model where the mean is 1103, what value is here on the axis that would give me a 0.58 over here? So we're going to go second distribution, inverse norm, 0.58, mean is 1103, and the standard deviation is 82. $1119.6. Whole number, so 1120. Weight representing the 98th percentile. So the same thing, but this is now going to be a 0.98. So let's just change that to 0.98. And we get 1271. and the interquartile range for the weights of these steers. So for the interquartile range, what I need to know is the 25th percentile. So what has a 0.25 here? And the 75th percentile. So 75th percentile would be 0.25 here and 0.5 here, right? So I want to know those two values. So let's do them one at a time. So the same value, but we're going to change that 98 to a 0.25. 1048. Oh, I'm sorry. 1048 is this value here. I need to write that down. And then the one over here, we're going to do the same thing, but 75. $11.58. So I want to go 1158 minus 1048, and that's my interquartile range, 110 pounds. The cholesterol levels of an adult can be described by a normal model with a mean of 189 and a standard deviation of 27. Let's find that normal model. So we need 189 in the middle. They've all got that. And then 27 up. So we'll go quickly. 27 times 3 plus the mean, which was 189, is 270. So my top number on these should be 270. This is the only one that is. What percent of adults do you expect to have a cholesterol levels over 200? So what I'm doing here is we're saying 200 right here. Well, no, not there, sorry. 200's right here. So I want to know the percentage going this way. So I'm going to do the normal CDF. My lower is the 200. The upper is going to be infinity. My mean is 189. And my standard deviation was 27. And we get 34.2%, 34.19%. What percent of adults do you expect to have cholesterols between 140 and 180? So we're going to go second distribution, normal CDF, 140 to 180. Same mean, same standard deviation. We get 33.47%. Estimate the interquartile range of cholesterol levels. Okay. So let's find the 25th percentile. So we're going to go second distribution, inverse norm, the 25th percentile, so 0.25, mean of 189, and the standard deviation of 27. And that's 170. Now let's do the same thing. for the 75th percentile. And we get 207. So between 170 and 207. Nearest integer, so I want to go 207 minus 170 is about 37. Above what value are the highest 15% of adult cholesterol levels? So I want to know if my mean is 189, what number is here so that 0.15 is over here? So we're going to go second distribution, inverse norm, 0.15, 189, 27, and it's on the right. 216.98. So nearest integer would be 217. Companies who design furniture for elementary school classrooms produce a variety of sizes for kids of different ages. Suppose the heights of kindergarten children can be described by a normal model with a mean of 39.2 and a standard deviation of 1.9. What fraction of kindergarten kids should the company expect to be less than 35 inches tall? All right, so we've got a mean at 39.2. Here's 35. Less than 35 inches is going this way. So I want to do normal CDF, negative infinity, up to 35, with a mean of 39.2 and a standard deviation of 1.9. That's about 1.35. So about 1.4. In what height interval should the company expect to find the middle 70% of kindergartners? So, in other words, what number would be here? Whoops. What number would be here and here so that this is a 0.7? Well, if that's a 0.7, 0.3 is on the outside, and 0.3 cut in half would mean 0.15 here and 0.15 here. So I can do 0.15 on the left. So second distribution, inverse norm, 0.15 with a mean of 39.2 and a standard deviation of 1.9. And that's on the left. And that gives me 37.23. And then I can do 0.15 on the right. So second distribution, inverse norm. Everything is the same, but I want to choose on the right. So 41.16. So to one decimal place? Okay. So we're going to go 37.2 to 41.2. At least how tall are the biggest 10% of kindergartners? So the biggest 10% would mean what number is here? Whoops. What number is here so that this is a 0.1? So we're going to go on the right, so I can use that one. And let's just change that 0.15 to a 0.1. $41.6. Shifting data by adding a constant to each data value does not change. Okay, If I shift everything up, that will shift the quartile up. It'll shift the mean up. It'll shift the median up. But the standard deviation is still the deviation away from that shifted mean. So it stays the same. Which of the following statements is true about a z-score? Z-scores have a mean of 0 and a standard deviation of 1. That is true. Z-scores standardize a data set. That is true. Z-scores tell us how many standard deviations a value is from the mean. That is true. A z-score is a measure of how extreme or how typical a data value is. That is true. So all of the above. Jody, a statistics major, grows tomatoes in her spare time. She measures the diameters of each tomato. Assume the normal model is appropriate. One tomato was in the 50th percentile. What was its z-score? So my 50th percentile, remember, on a normal model means what score is here so that 50% is on the left. Well, that's the mean, right? So whatever our mean is, that would be the 50th percentile. So this is asking what's the z-score for the mean, and we know the z-score for the mean is a 0. All right, guys, you should be able to do your homework. Don't forget you have that quiz that's due, and I'll talk to you guys soon.